questions going. But.
Okay. And again, we are at this point recording this session. And today, fellows, we will be talking about the Simplicity SSE Control as we kind of open up our PowerPoint here. And we're going to ask that everybody do take some good detailed notes with our, let's see here, get a few more things going with the old PowerPoint here. So everyone should be able to see the Simplicity SSE Control Overview, the first slide on our little PowerPoint. Guy, I'll let you kind of be the monitor on that. Does that look good for you guys?
You're good.
Okay, fantastic. And as I said, I'm not sure how many people we're going to have, but in all fairness, I've got about 2 minutes before the top of the hour. So if that's okay with everybody, we'll go ahead and wait till 8 o'clock sharp before we get started to give whoever's going to get the opportunity to come on to go ahead and get on. So about another minute now, it looks like. Now, Guy, just curious on the presentation, because I've never been on the back end of it here. Am I somewhere? Is there a little video of me somewhere streaming as well, like in the lower corner or something?
Yes, there is.
Okay. Well, fellas, I'm going to encourage everybody to please ask those good questions. Again, we are doing a recorded session, and but please don't be shy. Just unmute your mics and ask those good questions. I will ask at this time that you go ahead and mute your mic, and I'll give everybody plenty of opportunity to ask those questions at the appropriate places. But sometimes what happens when we have you guys mute your mic, it seems to decrease the amount of echo in the background. But that doesn't mean don't ask good questions. If you got a question, unmute that mic, and we'll go ahead and answer that question for you. So, fellas, I've got 8 o'clock at the top of the hour, so let's go ahead and get started with our training this morning. At this time, we're actually going to be reviewing the SSE control board layout. Now, one of the things I decided to do when I did this training, it's more towards a technical basis or a technician's point of view. There's a lot of things this board will do. We're going to be talking about some of the features of the board, but this is going to be just a really good control board layout. Every input and every output will be talked about. And I'm going to ask that you please follow along and take some detailed notes as we discuss some of these following key points. As I've mentioned, we're going to talk about that 24-volt input to the board and the SD, or the smoke detector safety circuit. We've had a little bit of confusion in the field as to what that is and how to hook that up. So we're going to talk about that. And we'll talk about how it comes from the factory with just a jumper that you can remove and put safety circuits in there. We're going to talk about the thermostat and limit controls. Conventional thermostat hookup, we have found that most of our wind supply location customers are utilizing just a conventional thermostat. Likewise, this board typically comes from the factory set up for thermostat only enable. But I say typically because I've yet to find one that didn't come that way, but still it's one of the things we want to be sure and check if we're having some erratic operation or the thermostat doesn't seem to be communicating, or not communicating, but doesn't seem to be working. We want to make sure and go to that thermostat only enable function, which we'll show you how towards the end of the class. We're going to talk about sensor inputs with the corresponding voltages and the USB access port. We're going to get into all the outputs, including pressure switches and the SA, also called the sensor actuator bus. We're going to talk about that user display and how to get into it. You're going to have some enter buttons and a cancel button and a joystick and a couple of other things like that. In addition, you're going to notice there's a little 6-pin plug that's a parallel port to the SA bus. Now, if you haven't looked at it or heard much about it, by all means, one of the things I'm going to encourage you to do if you're working on these SSE control boards a lot is to invest in what we call a MAP device, a MAP, MAP device. And that MAP stands for Mobile Access Portal. And what it is just a little tool that basically you can carry around with you. And it's you plug it into this 6-pin SA bus, this parallel port that we're talking about on my last bullet point there. You plug it in, and what will happen, it becomes a portable Wi-Fi access into that piece of equipment. So you can take a smartphone, you can take an iPad, you can take your computer, because what that little map device becomes, it becomes a portable Wi-Fi and direct access into that control board. And it has a line of sight capability of about 300 feet. So you could be sitting there in your work truck and you can access the equipment, so you don't have to stand out there in the rain. And if you're inside a building, it has about a 100-foot range if you're inside the building. So it's a very, very, very slick tool. And by all means, I'd encourage you to consider that if you're doing a lot of work on the SE controls, or if you're putting a lot of commercial equipment in. It's a great tool to have. I've got a couple here with my hands-on trainers that I utilize when I'm playing around with the hands-on trainers, as I kind of refresh myself on the SE control myself. So, fellas, what we're going to do, we're going to be taking segments of the board, and we're going to take them and kind of blow them up into a larger screen, if you will, or into a larger PowerPoint slide. And then we're going to literally go over every input and every output and every sensor input on this board. So hopefully at the conclusion of this training, you'll have a better understanding what hooks up where, as well as what those functions do, as we kind of dig into the board and talk about some of the key features of the board. So that first section, if you were to take a board and you were to take all the wires off of it for training purposes, and you were to blow up a section of that board, let's go ahead and do that. So we're going to start at this upper left-hand corner of the board, if you were looking at it like we see in the photo. If we take that upper left-hand section and blow that up, we're going to talk about some of the features of that board, a little graphic, and then we'll actually blow the picture up as well and talk about each terminal on the thermostat. So this first thing I always like to talk about is this simplified block diagram about the 24-volt input to the board and the SD circuit. So as you take a look at this little block diagram, you'll see that there's a transformer, primary and secondary, and that's your 24 volt. It's a 75 VA transformer. It's also protected by a 3.2 amp circuit breaker. And so that voltage at 24 volts goes to 24 V and C. Now, it should be noted, this is an important concept. Unlike our competitors, that when they have a problem, say a smoke alarm or something like that, they shut all the 24 volts down and they kill the microprocessor. We don't do that. What we do is we keep the microprocessor alive, so to speak. So you'll notice that even if you have a smoke detection, his little brain is still working. So the microprocessor is powered all the time. Anytime you have 24 volts, or more specifically, anytime you have power to the unit, you're going to have 24 volts on C and 24 V to power up the microprocessor. Now, as you take a look at this little block diagram from the 24 V portion over to 24 SD and SDR, so SD24 and SDR, that's your smoke detector circuit. Now, fellas, it should be noted from the factory, if you do not have a factory installed smoke detector or phase monitor or other sort of shutdown system, what you're going to have from the factory between SD24 and SDR is going to be just a red jumper, and it typically sticks out about 1 inch. And it's very, very distinct. It's just a red jumper that goes between SD24 and SDR. Now, this is called the smoke detector circuit, but from a generic standpoint, it's that SDR and SD24 circuitry is really your safety circuit. So you can remove that jumper if you want in the field, and you can put any sort of dry relay alarm contacts between SD24 and SDR. You could have a phase monitor, a smoke detector. You could have a big old fireman switch. You could have a big red button where you hit it and it shuts the unit, whatever you want to do. You could have a condensate overflow switch. The main thing we got to remember, that switch has to be a dry relay output. In other words, it's going to be just a click, 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 a set of contacts. You don't want to have like an electronic sensor, or you don't want to have one of those little time delay relays that are electronic, because that could screw it up. It won't hurt anything or burn anything up, but it may not be reliable. So that SD24 and that SDR circuitry, that safety circuit, you pull that jumper off, put whatever you want in there as long as they're dry, click, click, normally closed relay contacts. Any questions or comments on that little circuitry real quick before we move on?
No, we're good.
Okay, good, excellent. Another little side note, if you're getting erratic operation there's a couple things. There's three things I want you guys to remember. If you're getting a little erratic operation, says the SD circuit is open. Gee whiz, how come it's there's nothing on the SD circuit? Two things. Number one, or actually three things. The first and foremost, that circuit has to be closed electrically in order for the unit to work. So you have to have a solid physical electrical connection between SD24 and SDR in order for the unit to work. Now, the microprocessor will still be alive, but the unit will be dead. And so just kind of keep that in perspective. The other thing is that if you're getting erratic operation on a gas pack, make sure you have really good grounding. And if it's not a gas pack, make sure that all your limits are closed and you have that red jumper there, or you've got a dry set of contacts in that SD24 and SDR. So those are just a couple little things that we've found in the field, that if you're getting that SD24 fault, check grounding. Make sure you got a good solid connection there between SD24 and SDR. And then finally, make sure you've got your 24 volts on your microprocessor and so on. So just keep that in mind. It's a safety circuit, and it has to be closed in order for the unit to work. Oh, let's blow that section of that board up again that we talked about a minute ago into a larger slide here. So starting at the upper left-hand corner of this section of the board, you're going to notice there's a limit. It says limit. Now, it should be noted that's 24 volt input from the heat section, and it has to be present at all times. Now, this is kind of an interesting point, because let's say it's in the dead of summertime and you're in the cooling season. Why in the world would that limit have to be closed? Well, it's a safety limit that's going to be monitored year round. And so you have to have 24 volt on that limit from the heating section to prove that the heating section doesn't have an open limit. Even if it's in the cooling mode, that still has to have 24 volt on it at all times. As we move down the left-hand side of the board, we've removed the terminals, the little screw terminals, so that you can see the spade terminals a little bit better. But this is where your thermostat hooks up. And so if you have a conventional thermostat, you'll be hooking it up on these terminals right here. And so it's very, very conventional. W1 is first stage heating input. W2 is your second stage heating input. One is first stage cooling on a two-stage product. G is your fan call. And again, this is very, very conventional in our industry. Nothing unusual here so far. Y2 is your second stage cooling input. Now, this is where we start getting a little bit, unique in the fact that it's just some of the features of our control board, our Champion control board. The OCC is a 24 input for occupied mode. So if you have a thermostat that has the capability of occupied, unoccupied mode, you can utilize this to tell the board it's occupied or unoccupied. If you do not use this circuitry, this is just a little field tip, and you're on a conventional thermostat, what I like to have contractors do is put a permanent jumper between OCC and R, 24 volt hot. And what that does, when you put a permanent jumper between OCC and R, 24 volt hot, it tells the board, or it kind of tricks the board into thinking it's occupied all the time. And then it's just going to be strictly driven by thermostat input. Now, if you don't put that jumper there, is it going to work? Absolutely. But we have found that on a conventional 24 volt thermostat hookup, the board likes to be occupied. And so now basically at that point, unless you have an occupied, unoccupied function on the thermostat, then go ahead and just jumper that, and that'll give you what seems to be a little more reliable operation. And that was a field tip that we were giving everybody a couple of years ago. If you're on a conventional thermostat, go ahead and do that jumper. Any questions or comments on that so far?
Not on that, Joe. I do have a question on the SE 24 and SDR.
Okay.
When you're in that mode and there's a fault on that, and you know that it's a closed circuit, is there only repair on the board?
Is there only what on the board?
Is there only repair to replace the board? You know that's is jumped and you're good, there's nothing in line.
That's a good question. So if you're getting an SD24 fault, and again, you have to remember that the trigger on that fault is not just to open close. Even though we, as electricians or as technicians, let me shut that fan off back there, sounding a little bit of noise. But as electricians and technicians, when we think about an input to a board, a dry relay input, we think, a 24 to 27 volt. And when we think about an open circuit, we think about 0 volts. However, it should be noted that the electronics on this board actually have a trigger voltage of somewhere, I'm thinking around 18 or 19 volts. So in other words, if you've got 19 volts between SD24 and SDR, it may trigger the board as an open circuit. So I want you to catch this now. So one of the things that I always encourage everybody to do is that double check your line voltage. Double check your line voltage feeding the 24 volt transformer on the job site. And we always ship our transformers on the highest voltage they're capable of. So let's say it's a 240 volt system and it's got a 208, 240 volt transformer, primary, transformer tap on this unit. And so you get on the job site and and by the way, we always ship that transformer on the 240 volt tap, primary tap. So you get on the job site and you find out that your actual line voltage is, I don't know, say 212. It's not 208, but let's say it's 212, 213. And so the temptation would be, or let's say it's 217 or 216. So the temptation would be, well, I'll just leave it on the 240 volt tap. And so what happens is once you start loading the low voltage control circuitry down, especially like on a heat pump, with a reversing valve and stuff like that, that low voltage can dip down. That low voltage can dip down to like 17, 18 volts or 19 volts, and it may be enough to trigger that SD24 SDR circuit, even though there's a hard physical wire on there. If your low voltage control voltage dips down to around that 19 volts, it can trigger the electronics into thinking it's an open circuit. Even though it's not an open circuit, there's a threshold in the electronics that perceive that as an open circuit. Does that make sense to everybody? So that being the case, the first thing I always check is grounding, because we ground one side of the transformer, we call it common. But make sure you have good grounding, and then triple check that transformer, that your low voltage transformer is on the proper tap. Now, when I say proper tap, we ship it on 240 volt, and let's say your job site, your actual line voltage is 216. Put it on the 208 volt tap. And so, and most of the time that cures that. So other than that, to your good question, I know I'm kind of expanding it and get a little long-winded, but to your good question, so double check your low voltage. That's absolutely critical, that with that unit just sitting there, you should read more like about 26 to 28 volts with nothing on. But with everything running, with the low voltage going, the thermostat going, if it's a heat pump, the reversing valve is energized and cooling and all that, you should never drop below 24 to 25 volts with everything running. And so adjust that primary transformer tap. And even if it's kind of an odd voltage, actual line voltage is like 217 or 212 or 214, something like that, put it on the 208 volt tap. And then what that'll do, that'll ensure that you, and by the way, this board will handle up to 35 volts, up to 35 volt low voltage without any problem at all, I've been told, even though the nominal voltage is 24. So double check your connection, make sure there's no loose connection on that jumper wire between SD24 and SDR, and then that low voltage and grounding are the top things I'd ask you to do if you're having issues with that intermittent SD24 and SDR fault. Excellent question. Any other good questions? Okay, so fellas, as we move down the board on the thermostat side, there's an X terminal. That X terminal is an output from the board to the thermostat to indicate a fault. So if you've got a fault on the board, it'll actually output a 24-volt signal. It'll just click a relay. It'll output a 24-volt signal on that X terminal to alert that there's a problem on the board. Now, it should be noted that this is only going to work if your thermostat is equipped with a fault light. So if you've got a 24-volt thermostat that has a fault light, you can hook that X wire to it, and it'll just flash that fault light if you've got a fault on the board. So it's strictly an output to the board, has nothing to do with the function of the board. It's strictly an output from the board to indicate a fault. It's a fault reporting circuit. Below that is our 24-volt hot to the thermostat, that R terminal. Again, that's extremely common, if you will, in our industry. R is 24-volt hot. Now you'll notice that on the terminals, on the thermostat terminals, there's a parallel SD24 circuit. And I'm going to recommend that now it may be used for field installed safety devices, but what I'm going to recommend is just leave that alone, even though it's if you look at that block diagram in that previous slide, it's just a parallel circuit. So one of the things I'm going to ask that you do is just leave that terminal open. Don't do anything with it. Instead, go up there to the top part of the board where we've been discussing the SD24 and the SDR. Remove that jumper at the top of the board, and then put your safety circuits, your aftermarket or your field installed safety circuits up there. Don't mess around with it down there by the thermostat terminals. A more reliable place is to go up to the SD24 and SDR jumper that we've talked about if you want to put field installed dry relay click switches in there for safety circuits. Any questions or comments on that? Okay, and then the last terminal on our 24-volt thermostat hookup terminals is C, 24-volt common. And it should be noted, we take one side of our low voltage transformer on the 24-volt side, and we take it to ground, and we call that common. So 24-volt common is actually reference to chassis ground. As we move up towards the top of the board, this is where we bring power into the board. There's that C and 24V. That's what powers up the board. Now remember, guys, this is where your transformer is actually going to be hooking up, is between C and 24V. And it powers the microprocessor all the time. Even if the unit is shut down by the SD24 and SDR circuit, if that circuit's open and the unit is non-operational, you're still going to have power to power up his brain. And so that's the way our engineers have designed this. And I really like that, because now if you have a fault on the board, even though you're in a shutdown condition, you can still read that fault on the user display because we have power to the board all the time. Even in a shutdown scenario, we've got power to the board, so the microprocessor can still think and tell us what's going on. Any questions or comments on that? Is everybody good? Guy, can you still hear me okay?
All good, Joe.
You got it, amigo. Thank you. Okay, fellas, and then right there, right next to that is your SD24 and SDR used to power up your smoke detector and field installed safety circuits. And again, one more time, if you'll just make a note of this, that they have to be dry relay click switch type of contacts. You don't want to use like an electronic switching device or anything like that. Just use any alarm contacts, any aftermarket alarm contacts you can put in there. You can put a fireman key in there. You can put whatever you want in there. Right next to that is an R output. This is an auxiliary 24-volt output, 24-volt hot for other unit components. So from the factory, you may see something hooked up to that R terminal, or it may just be open as well. So just, based on the tonnage of the unit and so on, you may or may not have anything hooked up to that from the factory. Okay, the next area we're going to talk about is going to be sensors and voltages on those sensors, as well as the USB port. And so again, if you're kind of looking at the board, we're going to segment that board we're going to take a hunk of that board, pull it out and blow it up, and then talk about all of those functions. Now, one of the things I like to encourage everybody to do, especially when you're talking about using sensors and checking sensors, is that a service technician is going to have a good high quality volt ohm meter. And I'm going to recommend that you buy one that has what we call true RMS capability. as well as the normal ohm and voltage functions. Now, I'm not trying to sell any product or anything like that. I don't mean it to look this way. It just so happens this is my own personal meter, so that's why I took a picture of it. But by all means, there's lots of different manufacturers out there that have really good tools. Field Piece, Fluke, or just to name a few, Testo. They all make good meters. But we're going to make sure that the technicians, if he's going to be working on the simplicity control, he's going to need to be able to take DC voltages and AC voltages to properly diagnose, especially sensors. In addition, I'm going to recommend that you buy a set of needlepoint meter leads. Again, what you're looking at right here are tools out of my own personal tool bag. And those needlepoint meter leads, you'll notice on the right-hand side there, they're extremely sharp. They're literally a needlepoint meter lead, and that works really, really well for taking live voltages down into a harness. So if you've got a harness plugged into a sensor, or you've got a harness plugged in, like on your thermostat inputs or whatever, you can take those little needlepoint leads and you can dig them down inside that sensor harness, and you can read what the voltage is on that harness with the sensor plugged in. So it's extremely handy. And so those are some recommended tools that we recommend the technicians use and have, especially the needlepoint meter leads, and then of course whatever meter they like, but they need to be able to read DC voltage as well as ohms and those other valuable information on sensors. Now on those sensors, again, you're going to notice that there's a sensor chart, and that sensor chart, you're going to find it typically in your install information with the equipment. And you'll notice that sensor chart is designed to be set up in such a way that it's going to be a temperature and a resistance and a voltage at any given temperature. To give an example, so if I'm looking at this sensor chart and I want to know what the pin-to-pin voltage, in other words, with the sensor plugged in and with my needlepoint meter leads, let's say at 0 degrees as an example, as you take a look at our screen, at 0 degree temperature Fahrenheit, if I was to take my needlepoint meter leads with the sensor plugged in and read the DC voltage on that sensor with it plugged in, it should be 3 volts DC. If I took that sensor off the board and I took my ohm meter and I ohmed it out, it should be 85,398 ohms with the sensor just with the harness in your hand. You unplug the sensor and ohm it out. So that's the basic check that you're going to do. You're going to look at the temperature, measure the temperature that sensor is subject to. You're then going to take your needlepoint meter leads and go in, and you're going to read the DC voltage on that sensor with it plugged in and read the pin-to-pin voltage. And then you're going to unplug the sensor from the board, and you can then ohm it out to see if the ohms is close to chart value. Now, it should be noted, it should be within about 5%. And so if you're within about 5% of the chart value, you're plenty close. It should be noted that at 75 degrees, if you find 75 degrees, the nominal calibration point for our sensors is right at 10,000 ohms at 75 degrees, or very, very close to it. So that's kind of something you can kind of drill in your brain. If I take any of the sensors on my simplicity control, any of the sensors, and I subject them to 75 degrees, they should read around 10,000 ohms. And so you can kind of look at this chart and you can see that as the temperature changes, the voltage pin to pin changes, and the ohms change based on the temperature. Now, it should be noted, if I take that sensor off the board, the open circuit voltage at the upper left-hand corner of this chart tells you open circuit. What that means, if I pull the sensor off the board and I read the voltage on the pins that the sensor plugged onto on the board, it should read 3.625 volts DC without the sensor plugged on. And then according to temperature, you'll read a different voltage. And according to temperature, you'll read a different resistance on each sensor. So I guess what I'm driving at is that there's no mystery here. The sensors are very, very straightforward. They have a nominal calibration point of 75 degrees at 10,000 ohms at 75 degrees, or real close to 10,000 ohms. So there's no big mystery on the simplicity control. A lot of times technicians, they get it in their head, oh, this is a very, very hard control, all these sensors, what do I do? It's very, very simple. The same tools you've been using all along, in your truck, your voltmeter and your ohm meter, they still work. We just recommend needlepoint meter leads so you can read those voltages. Or you can take your map device and plug it in and get a lot of this information as well, as far as temperature and what it's reading and stuff like that. So please keep that in the back of your brain. If you're going to be using and you're going to be working on the simplicity control, make sure you've got good tools. And I recommend that map device, that mobile access portal, if you're doing a lot of work on them, where you can have easy access by way of your iPhone or your smart device with that map device. Any questions or comments so far before we continue?
No, we're good.
Good. All right, fellas. Well, let's continue then. So here's that section of the board that we blew up, and now again we're going to talk about some sensors and stuff like that. So you'll kind of see that if I pull those harnesses off, I can actually read the voltage on the sensor inputs, those pins with my DC voltmeter. So starting at the upper left-hand corner in this section of the board, ST is a space temperature sensor. Now, like all of our temperature sensors that we're going to be talking about, the nominal calibration point is 10,000 ohms at 77 degrees. Please excuse me, I said 75 before, so let me make that quick correction. Space temperature sensor is 10,000 ohms at 77 degrees, not 75. Now, that space temperature sensor is going to be used for sensing space temperature. Now, it should be noted that space temperature sensor is not needed for thermostat operation. However, the board still monitors and looks for an input on ST. So sometimes, especially on older equipment, even though you're on a thermostat, has nothing to do with the unit operation. If it does not see, or if it cannot see a space temperature sensor, then what will happen, it'll flash a little code and it'll say space temperature sensor unreliable or something like that. Even though the unit's working perfectly fine, you'll have this little light flashing and you'll have the little display said can't see space temperature. And of course, the technician, the first thing in his mind, oh, there's something wrong with the equipment. No, it's just that on some versions of some boards, if they don't see the space temperature sensor, even though they're working on a thermostat, it's still going to alert the technician that, hey, I can't see space temp. So if you want to get rid of that little light, even though you're on a thermostat, you can take just a standard, that little Honeywell space temperature sensor, run 2 thermostat wires from it, and they're non-polarity sensitive, so it doesn't matter which one hooks where, but you take a space temperature sensor, put it somewhere in the space or put it in the return air duct, and hook it up between ST and common right next to it. ST and common, and then that'll get rid of that little light. As far as the board's concerned now, can see a space temperature. So that was actually an early version of this board complaint we used to get. The technicians would call and say, hey, there's something wrong with the board. I'm getting this alert that they can't see space temperature. First thing out of my mouth as a tech head is, are you running it on a thermostat? Well, yes, we are. Okay, ignore the light. Well, we don't like the light. Okay, we'll take a space temperature sensor and put it between ST and common to get rid of the little light. And now the board is happy because it can see space temp, even though it's being driven by the thermostat. Any questions or comments or any observations in the field on what I've just described? Okay, now here's another little cool thing. So let's say, for instance, you've got the space temperature sensor in the space hooked up to ST and common. Now, let's say, for instance, hypothetically, it's in a nursing home or someplace, and it's a weekend, and so on. It's an emergency situation, and the thermostat goes bad. Watch this. If you've got a space temperature sensor in the space hooked up to ST and common, even though you're running off a thermostat, if that thermostat should fail, you can go down to the user display and you can set the user display up on the board itself and tell the board the types of temperatures you want to maintain in the space. And then when you do that, so you'll go to thermostat only, no, and then it'll start looking at that space temperature sensor to drive the temperatures in the space. Isn't that the coolest thing? So so I like putting a space temperature sensor in a space for 2 reasons. One, it gets rid of the little red light, but also if you have an emergency situation, the thermostat goes bad, you know, you got some broken wires behind the wall, whatever the scenario is, you can actually go to our champion piece of equipment with a space temperature sensor in the space, and you can program that board to maintain any particular cooling or heating set points that you want. The thing will sit here and run all by itself, just looking at space temperature all day long, and it gives you some nice emergency, emergency function if you lose your thermostat. Any questions or comments or anything about that little field tip? Any questions on that? Okay, well, right next to ST and common, there's another little input. It's called a space sensor offset, and this is a variable resistor or a potentiometer, 0 to 20,000 ohms. And what that's going to be for is going to be if you've got like a building management system on the board, you can use that SSO offset to help offset any temperature differentials from the actual thermostat or on the, not the thermostat, but the sensor where it's setting in the space. Typically, this is not used with a conventional thermostat, but just for a point of education, it is a space sensor offset that you can put in there with a variable resistor on a building management system. Right next to that, you have a 2-pin output, input-output, and this is a supply air temperature sensor. Again, 10,000 ohms at 77 degrees. It is required for operation. So this is a supply air temperature sensor that comes from the factory hooked up on the unit. Right next to that is a return air temperature sensor. And again, this is required for operation, and it's going to be used in enthalpy calculations. It will also be used if you lose your space temperature. So if you lose space temperature sensor, the unit will default. Now, this is presuming you're not on a conventional thermostat. You're like on a building management system, or you're driving the unit by the user display, not a thermostat. What will happen, it'll look at return air temperature, and you can actually operate the equipment on return air temperature if you don't have a space temperature sensor or the thermostat fails. And so this is required for operation. And so make sure that, again, that sensor is viable when you're doing your troubleshooting. From the factory, you also have an outdoor temperature sensor. And again, all of these sensors, team, are 10,000 ohms at 77 degrees. And this is also required for operation. So that supply air temperature sensor, return air temperature sensor, outdoor air temperature sensor, they're all wired in from the factory, and they are required for operation. It's also used for low ambient cooling and as part of the heat pump defrost cycle on a heat pump. So those 3 sensors right there. Again, return air temperature, supply air temp, and outdoor air temperature sensors. Those are all required for operation. Any questions or comments on those so far? Okay, next to our outdoor air temperature sensor, we're going to have another harness, and we're going to have a condenser coil number 1. It's a sensor input to looking at the condenser coil. It will be required for heat pump defrost operation, and it's optional on straight air conditioning units. Right next to him is the evaporator coil temperature sensor, and it is required for operation. And what it is basically a suction line temperature safety. So if you start frosting or icing up the coil, the evaporator coil, because you have low airflow or a dirty filter, what will happen is this sensor will see that, and it'll act accordingly. So it is required for operation. It's an evaporator coil sensor. Now, if I have a 2-stage piece of equipment where I have 2 evaporators and 2 condenser circuits, then these next 2 sensors make sense. So a CC2 would be condenser coil number 2. If I have a 2-stage unit, works the same way. And it is required for 2-stage heat pump defrost operation if it's on a heat pump. Right next to him is EC2, which is evaporator coil temperature sensor. And it's required for 2-stage operation as well. So again, team, remember, if you only have a single-stage unit, you will not have sensors on CC2 and EC2. But if you have a 2-stage piece of equipment, you'll have sensors on both condensers and both evaporators. Is there any questions or comments on our sensor layout?
Hey, John, those sensors you have there, outdoor fails, you jump that field to get by.
Oh, that's an excellent question. No, as a matter of fact, that's an excellent question. So if I was to jumper that sensor, what would happen? If I jumpered it, is it would interpret that as an extremely low ohm value. And if you take a look at our sensor chart that we just talked about, we find that you have real high ohms. It's a negative coefficient thermistors. So you have real high ohms when it's cold, and then very low ohms when it's hot. It's exactly opposite of a normal thermistor. So basically, if you jumpered it, it would think that sensor was, I don't know, pick a number, 300 degrees or something like that. And so that's a very good question. So no, if you have a faulty sensor, you're going to have to replace that sensor, and you are not able to jumper that. Thank you for that good question. And because if you jumpered it, it would interpret that as 0 ohms or very low ohms, and then that sensor again would think it's like 300 degrees or something like that. So good question. Any other good questions or comments about that? Good question. All right, team. Now remember, all temperature sensors have a calibration point of 10,000 ohms at 77 degrees. Open circuit voltage. In other words, if I remove the harness from any of these sensors and take the voltage on the pins where those sensors hook up, it should be 3.625 volt DC. And then again, we could refer to that sensor chart we talked a little about to determine if the sensor is operational. And as the last little point, remember, if you have an optional SSO sensor, an SSO, space offset, it's 0 to 20,000 ohms with that potentiometer or that variable resistor. All right, as we come down the right-hand side of the board, we have a return air humidity sensor that's going to be used for enthalpy calculations and economizer calculations. And that return air humidity sensor is a 0 to 10 volt input from a sensor, a relative humidity sensor, and that's an optional input, so that it doesn't come from the factory at that unless you've got some factory installed options that require that return air humidity sensor. Right down below that is another input. It's a duct pressure sensor, and it's an input from a supply duct pressure sensor, which is again is optional. So if you have a requirement, a particular architect or engineer building requirement where you have to have a duct pressure sensor, this is where you'd hook that up. Here we have a dirty filter switch. It's a 24 input output. It's a 2-pin connection, and it's used to detect a dirty air filter. And again, this is strictly an optional thing that you can do on the board. And by the way, while I'm thinking about that, one of the things I really, really like about our Champion Johnson Controls setup, you don't have to use all these optional functions. But if you have a situation where the architect or the engineer is calling for, dirty filter switch or duct pressure sensor or whatever, we give you a place on the board to do that instead of having a bunch of complicated relays and extra stuff you have to buy and stuff like that. You can literally just take your little diaphragm dirty filter switch, which is nothing more than just a little diaphragm switch that looks at pressure differential across the filter switch, and hook it right there on the board. And what it'll do, it'll monitor that pressure switch for you. And the board's smart enough to know that if it sees that it's monitoring it, and it'll actually give you a display on your user display if you have a problem. Or if you've got the map device, you can hook the map device in, take your smartphone, your smart device, your iPad, and you can go in and access all that information with your smartphone as well with the map device. As we move down the board, we have an air proving switch. And again, this is a 24 volt input output, and it confirms blower operation. And again, it doesn't come from the factory at this unless it's ordered, or more specifically, if you have a building requirement for this, this is where you'd put an air proving switch if that was required by the engineer or the architect. As we move down the board, we have a C. This is a onboard common for variable frequency drive output to the variable frequency drive motor. So this is a VFD output. It's a common for the VFD output. Now watch this. If you've got a variable frequency drive blower, this VFD output from the board will be a 2 to 10 volt DC output to drive that variable frequency drive 0 to 100% airflow capacity. Right down below that, you'll have a VFD alarm. Now, it should be noted this is an open alarm circuit, which means a 24-volt input. A 24-volt input to that VFD fault results in unit shutdown. So let me say that one more time and stress this. This is an open alarm circuit, which means that when it's normal, there's nothing there. There's no voltage on there, normal condition. But if I have an alarm, my VFD will if I have an alarm, my VFD will output 24 volts. And if I put 24 volts, if I apply 24 volts AC on that VFD fault pin, it shuts the unit down. So it's kind of opposite of what you think an alarm circuit would be. We normally think about alarm circuits being normally closed, and then they open for alarm. Well, this is exactly opposite. Open circuit is normal. If I put 24 volts on it, it shuts the unit down. Any questions or comments on that? So if I take my voltmeter and everything's running good, I should not read voltage on that VFD. If I've got a variable frequency drive, I should not read 24 volts on that alarm circuit when it's running normal. Right next to him, or right around the corner from him, is a USB port. This is going to be used to access like a USB drive for backup and restore functions. And if you have software updates, you can plug that in and you can update your software. Now, team, I'm gonna recommend something, and this is again from the old tech head here. If you've got a unit, let's say it's a couple years old or a year old, whatever, and you're on a thermostat, you're running on a conventional thermostat, and the unit's working fine, there is absolutely no reason to go update the board. Let me say that again. If you're on a conventional thermostat and the unit's running fine, leave it alone. Because we've had some local contractors and local companies, they see there's an update in the board, they want to update the board, and those updates are typically going to be centered around like building management systems and BACnet and Metasys and all this different stuff. And the truth about it is, if you're on a simple, easy, simple, conventional 24-volt thermostat and the unit's running fine, leave it alone. There's no reason to update the board. That's just a little bit of a tech tip, because sometimes what will happen when you update the board, it forgets it's on a thermostat, and then you have to go back in and tell the board thermostat only enable yes and all that stuff. So if it's working, leave it alone. Questions or comments on that?
Hey Joe, along those lines, how many different boards are out there? Forget the software versions, but is there a two-stage board, a single-stage board, multiple two-stage boards?
There's essentially there's going to be a single stage and a two-stage board, and then there'll be an expansion board if you have like a four-stage unit, big commercial four-stage unit. Now, it should be noted, I believe that's an excellent question. I believe if you get a replacement board, if you have to warranty the board out, I think the replacement board is a universal board, which is going to be two-stage. And so depending on the unit, you'll basically have a customized board for that unit, single stage or two stage. And then, but if you buy a replacement board, you may notice that there's more relays on it that just aren't used. So instead of making 57 or 100 different replacement boards, they make essentially one replacement board that'll work on anything, if that makes any sense. Good, excellent question. Any other good questions? Okay. All right, let's take a look at the bottom of the board in our photo. We're going to take that, we're going to blow that up and talk about it. And as a matter of fact, if you take a look at this board, you're going to notice there's a whole bunch of relays right above where we're talking about. Those are the relays I'm talking about. So this board that you're looking at right here is probably a replacement board that I got for purposes of training. And so your actual board from the factory may have less relays. It might be a dedicated single stage board or whatever. But if you have a replacement board, it's going to look like this one, where it's got all those relays down on the bottom, and it's a universal board that'll work fine on any of the equipment And so that's, I believe what we're looking at is a replacement board in answer to that good previous question. So at the very, very bottom of the board, let's take a look at some of those inputs and outputs down below. And we'll blow that up and we see that, kind of expand that out, and starting at the right-hand side, this is a 24-volt output. And this could be, it depends on the tonnage of the unit. You may have an auxiliary output specific to an output, 24-volt output relay, a isolated relay output on that. So if you have a really big board, one transformer might not do it to run all the low voltage stuff. So sometimes what we'll do, we'll utilize this 24-volt output for other devices, and it is an isolated relay output. And again, it may be fed from a second transformer based on the size of the unit. You also may find that on your unit, if you have a little single stage unit, you may not have anything hooked up to that 24-volt output. So just be aware of that it's a 24-volt hot relay isolated output, and it may be operating things on a very large piece of equipment with a separate transformer, or it may not based on the tonnage of the unit. So just be aware of that. It's just a 24-volt output, isolated relay output. Right next to him, we have a H1 and H2, and this is a 24-volt output to the heating section on a unit that has a heat section for first and second stage heating calls. Right next to that is an MV 24-volt output for the heating section to confirm heating operation. So basically, this MV is an input from the heating section to tell the Simplicity control board, hey, we're working normally. So think about a gas pack for a second. So let's say I've got a gas pack, I call for heat, it goes through its normal sequence of operation, and once it confirms flame, and you have flame proving and all the stuff that a gas pack would have to have, it's going to output from the heating section to tell the motherboard, so to speak, hey, we're working okay. So that's what that is. That MV is an input from the heating section to confirm heating operation. As we move down across the board, we see that we've got a CN fan, and what this is a 24-volt output to the condenser fan contactor. So when, once all permissions are met, in other words, the switches are closed and we've got a thermostat call for operation and so on, once those permissions are met, the board will then output 24 volts on that pin to bring the condenser fan on for cooling operation, or if it's a heat pump, it'll bring the condenser fan on for heating operation as well. Here we have an auxiliary heat 24-volt output for hot gas reheat. So if your unit is equipped with a hot gas reheat solenoid, this is what energizes the hot gas reheat solenoid if it's so equipped. Next to him is a 24-volt output to our indoor blower. Now this is important. If you've got a conventional, just a three-phase belt drive motor in there, it's not a variable frequency drive, just a motor. This is going to output 24 volts to the indoor fan contactor. This is the control voltage for the contactor. And so it's a 24-volt output to the indoor blower contactor coil, or it could also go to a variable frequency drive enable relay. So the way to think about this, on a thermostat, when I get a G call, if all permissions are met, in other words, if the board, safeties are closed and all that stuff, and I get a G call from the thermostat, the board will interpret that as a command for fan. It'll then output 24 volts here to either bring a contactor on, to bring on a conventional fan motor, or it will put out 24 volts to a variable frequency drive enable relay to bring the fan on. So just think about this as basically the final output on a G call or a fan call. Right next to him is C1 and C2. This is a 24-volt output for our compressor contactor coils. So again, our compressors are going to come on with a contactor. This is what controls the contactor coils for first and second stage compressor operation. As we move to the left of all that, we see we've got some HSP2 and LSP2. This is where your pressure switches hook in. These are your safety pressure switches, your high pressure switch and a low pressure switch. And again, if you've got multi-stage equipment, you'll have more than one of these hooked up. So basically, if it's a single stage piece of equipment, you'll just have HPS1 and LPS1 hooked up on single stage equipment. For low pressure switch and high pressure switches, this is your refrigeration safety circuits. And then if you have a two-stage piece of equipment, it'll be the LPS2 and the HPS2 will also be hooked up. Now, team, it should be noted that these safety circuits right here, this high and low pressure safety circuits, these are hard 24-volt safety circuits. Now, what I mean by that is if you open one of these circuits up, it results in compressor and unit shutdown. And so these are hard safety circuits. They're actually wired in just like a regular pressure switch. So it's just a click, click pressure switch, high pressure switch, low pressure switch, input to the board, and they are 24-volt input and output for those pressure circuits or those safety circuits. Any questions or comments so far? Okay, well, right next to that LPS1 is a fan overload. Now this is something kind of unique. You're going to notice that on our Champion equipment, on our commercial equipment, we're going to have another little set of wires coming off the indoor blower motor. They're typically, I think they're purple wires if memory serves me. But they go to this fan overload, and what it is, it's an indoor blower overload relay. And what it is, it's a safety device, and it has to be closed for fan operation. Now this is a little field tip. This is very important, so make a note of this or write this down. This fan overload is a 24-volt input-output, and that has to be closed electrically in order for the indoor blower to work. So let's say, for instance, the contractor, it's on a Sunday, and he's out in the country and whatever, and he's working at a plant, and he goes to his truck, and he doesn't have an exact OEM replacement motor. But he's got a motor that's the right phase and the right rotation and the right RPM and the right horsepower and the right voltage and so on his truck. We'll say it's a rescue motor, a type of rescue motor. But let's say that rescue motor does not have a fan overload on it, or that those auxiliary contacts on the fan as a safety circuit. It's really important if he uses a rescue motor or if he uses a non OEM motor as a replacement to get the unit going, I'm perfectly fine with that as long as the rotation and the RPM and everything is right on it. I'm okay with that. But just please remember, he's going to have to go down to this fan overload input, and he's going to cut his wires back, several inches so he can effect a repair later on. He's going to have to wire nut those harness wires together so that fan will run, because if that circuit is open electrically, you will not have a fan output on those previous pins we were talking about, and the indoor blower will not run. Any questions or comments on that?
Joe, when that typically faults, you're able to do a test through the VFD to see what type of fan it's in, correct?
So what this is, it's basically, if you take a look at our fan, our fan motors that we use, you're going to notice there's going to be like a little thermal disc on there. Now they call it a blower overload relay, but what it is just a little thermal disc. If it overheats, it's going to open electrically and shut the fan down is what it does. And so or like on the VFD, if the VFD has a thermal problem, it'll hit that fan overload, and then it'll drop out that little fan pin that we talked about earlier that outputs that 24 volts for fan operation. So this fan overload is strictly a safety circuit, and it's just a little thermal disc on the fan motor itself. So if you take a look at our fan motors, you're going to notice hey, what's those crazy little two wires off the back there by themselves? And I think they're purple wires. That's what it is. It's that fan overload. And so if you've got a replacement motor that doesn't have that, you'll sit here and scratch your head all day long. Why isn't the fan running? What's going on? Well, that fan overload has got to be closed electrically on the board in order for it to output fan on the pin, the FAN on the pin, to bring the contactor on. So drive you crazy unless you know that. Good question. Any other good questions or comments? Okay. Right next to the fan overload is you're going to have an SA bus. Now, this SA bus are going to be 4 hard terminals. And those terminals on the SA bus are going to be positive and negative, C for common, and power. So the positive and negative, the plus and minus, are going to be communicating terminals. And what will happen is if you have something on the SA bus, whether it's an economizer, or if you have your map device hooked up to it, by that little 6-pin plug, which we'll show you in a minute, which is just a parallel port on that SA bus. But the positive and the negative are going to be communicating, positive and negative communication terminals. And then the power terminal, the PWR, is a 15-volt DC plus polarity for bus circuits. The C is 24-volt common, which is basically a negative, or it pulls it to 0. Now, when it says negative, what it's really talking about is it's pulling that down to 0. So common is a reference to chassis ground. Power is 15-volt DC, reference to chassis ground. Plus and minus on the communication would be to communicate with things that are on the SA bus. And again, things that could be on the SA bus would be, for instance, like an economizer would be hooked up to the SA bus. And later on, when we look at that little 6-pin plug where we plug in our map device, it's actually communicating on the SA bus as well. Any questions on the SA bus before we continue? Is everybody good? Okay.
All good.
All right, so as we take a look at this next portion of the board, we're going to notice something. We're going to notice that there's a user display, and there's that little 6-pin plug I was talking about. Well, that little 6-pin plug that you see in the upper right-hand corner of this section of the board, that little 6-pin plug up there, that's where you plug in your map device, but it's just a parallel circuit. It's just a parallel port of the SA bus is what that is. So it's basically an auxiliary SA bus, that little 6-pin plug. As we take a look at the user display and all the stuff about that, let's talk about that some now. So the user display is an 8-digit 2-line display, and the user is able to access all the parameters on the system. And you can also read displays, and faults and alerts are also present, and it will actually scroll across that little user display. So again, it's an 8-digit 2-line display. You'll notice that when you power the board up, you're going to let it wait for a countdown. And typically it takes about 60 to 75 seconds if memory serves. It's been a while since I plugged in one of my trainers. But when you power that board up, the user display will be blank. Now on some models or some versions of the board, it'll say idle. So it'll either be blank or it'll say idle. And what that means is you're at the home screen right there. And if you don't have any faults on the board, it'll be either blank or it'll say idle, waiting for an input to the board, to call for operation. And this is normal screen. Now we're going to refer to this idle or blank screen as level 0 or the home screen. You're also going to notice there's going to be a power LED above it. And if there's something on the SA bus, it'll be flashing and communicating on where it says that little LED up above where it says SA bus. If there's something on the SA bus, excuse me, it'll be flashing as it communicates. So there's power. Anytime you have power to the board, you'll have that green LED on there. If you have a fault on the board or you have an alert, it'll flash that red LED, letting you know there's a fault or an alert.
Hey, Joe, on the faults, how long do it last? How do you clear?
How do you clear what, the fault?
Yes.
That's a good question. It's really going to depend on the fault or the alert. Most of them will clear themselves. And others, let's say, for instance, I've got a sensor fault. If I replace that sensor and power the board back up, it'll see that sensor is working again, and it'll clear itself. So most of the time, it'll fix itself. But on occasion, if you've got something that you have to, excuse me, if you take something like off the SA bus, and it can't, let's say you replace an economizer. Excuse me. Let's say you replace an economizer and it doesn't recognize the new economizer. You would go in and do what we call a relearn function, which would clear the board as it was like it was brand new, and then you would power it back up with the new economizer, and then you clear it that way. So most of the time you'll clear that fault just by fixing the component that's bad, and occasionally you have to go into the user display and do a relearn sequence, and then the board will relearn that it's just sitting there all by itself. And then when you plug the economizer on, as an example, it'll go out and see that economizer and then accept it, so to speak. So it really kind of depends on the fault that you have on how you do that. But yeah, that's a good question. We're going to get into the little buttons and the enter button and stuff like that, and that's actually how you access the user display. So if you have to clear a fault or do a relearn sequence, you can do it either by way of the map device that you have plugged into the little 6-pin plug, or the little buttons down below, what we're going to talk about here shortly. Good question. Again, the SA bus screen will be on or flashing. If there's something on the SA bus communicating with it, it'll be flashing. Now, team down below, we've got some buttons. Now, these buttons allow you to access the system parameters just by pushing buttons and moving a joystick. But let's go ahead and talk about those buttons at this time. So you're going to have an enter button. And what you're going to do, if you poke that enter button, it's going to accept the information that you've got entered in, or it's going to progress you to the next level. So remember, the home screen is level 0. And then based on the parameter we're looking at, you might have up to 5 or 6 different levels that you look at, and you get into those levels by poking the enter button. Or if you're in a level and you want to accept something, the enter button is what you do to accept that level. There's a cancel button. If you have the cancel button and you push it, you're going to go back to the previous level. If let's say you're on level 4, and I push the cancel button, it takes us back to level 3. It can also be used to cancel some selections by the user. So let's say you're in a parameter and you select something and you decide, well, I don't want that after all. I hit cancel. It'll then take you back to the previous condition or state. Generally speaking, the cancel button is going to be used mostly to get you back to the home screen. And fellas, go ahead and make a note of this, or write this down. If you're in doubt of where you are, let's say, for instance, you get sidetracked. You're working on a piece of equipment. You get a telephone call, and you get sidetracked. Oh, gee, what level was I at? Was I at level 2 or level 3? Doesn't matter. You start hitting that cancel button. Just cancel, 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 cancel. You just poke that button repeatedly. It'll take you back to level 0 or the home screen. In addition, if you're working on the unit and you get sidetracked and there's no, let's say you're in level 3 and you're doing something in level 3 and you get sidetracked and you're on the telephone for half an hour. After about 10 or 15 minutes, the unit will go back to home screen anyway. Okay, so basically if there's no input for like 10 or 15 minutes, it goes back to the home screen anyway. But a quick way to get to the home screen is cancel, 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 and that'll take you right back to the home screen. Now, right next to the cancel button is a joystick. Now, this joystick is going to be used to move a cursor. And when you take a look at the user display, you'll notice that cursor looks like a sideways V. Okay. And so that joystick, you can move it up and down, or you can move it left and right. Now, it should be noted, if you move it up and down, it allows you to check out different things in any particular level you happen to be in. If you move it left and right, what'll happen if you're in a parameter that you can change? In other words, if I've come to a point on my parameter that I can change it, and I move that joystick left and right, what'll happen, it'll cause the display to flash. So please burn this in your brain or write this down. Anytime you got a flashy display, that means you can change something. If the display is not flashing, you can't change it yet. You have to get to a portion of the parameter to where it's flashing. So when I get into a parameter that I can change, I move the joystick left and right. starts flashing, then I can change stuff. If it's not flashing, you can't change it. So that's an important thing to remember. Once you get into a parameter that you can change, you get the flashy screen. You select what you want, yes or no, or true or false. It just depends on the parameter, how they word it. It could be accept, it could be true, it could be false, it could be yes, no. So based on the parameter, for instance, like the thermostat only is a yes, no type of thing. And then you hit enter to lock it in. And normally the display will come up again and say, are you sure you want to keep this setting? You poke enter again. And then that sets it in. And then once you change a parameter, you always go back to home screen by what? Cancel, 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 cancel. That takes you back home as you kind of run back home to mama, so to speak, on the home screen. So that's how you use it. It took a lot longer to talk about it than it is to actually do it. But you have full access to the system with your enter, cancel, and joystick buttons. And it should be noted that you can also access everything by the little map device we talked about that you plug into that 6-pin plug up there. If you've got the map device and you want to use a smartphone or a smart device to access the equipment via the map device. But you don't have to have a map device. You can just walk up to the equipment and manipulate the enter, cancel, and joystick functions to get into all the parameters and the display. Any questions or comments so far?
No, good.
Okay. Well, fellas, I'll tell you what, let's talk a little bit about that SA bus. Again, that's a parallel circuit, and it's just a convenient phone type of circuit for alternate connections to the SA bus. And again, I really like the map device. You guys do what you want to do, but if you're going to be working on this equipment a lot, I recommend getting a map device, a mobile access portal. Okay, to use the parameter sheet. So there's these parameter sheets that I think I fired out some. It's just a little parameter sheet, and I apologize, the printing is quite small. But the parameter sheet, what it does, it's a little 4 or 5 page explanation of some stuff I put together some years ago, just to kind of help me. Did you guys get a copy of that, guy?
Joe, I have the parameters for the control itself. Yeah. And my question for you on that is there any chance you can talk to you guys about this and ask for an updated version? Some things have changed.
Okay, you're kind of breaking up a little bit there. Go ahead and ask it one more time.
So on the sheet where you show all the different settings for the controller,
Yes.
controller, so you say, hey, I want to go into return air temperature sensor, you go here and then you click to this one and get you out to the user paths.
Okay.
My question is there a newer version of that? Because it seems to have been updated since these were printed.
That's a good point, and I'm sure it has been. This parameter sheet that I've used for training is at least a couple years old, so that's an excellent point. There may be more parameters that they've put in, but the methodology is going to be the same as far as you'll have a full name description, a display name, and so on. So how you get in there is going to be universal regardless of any additional information they put in there or not. But yes, in answer to your question, there probably is an updated parameter sheet. I haven't asked our technical support people for one for a while, but I'll put that on my to-do list. In fact, I'll make a note right now that I'll see if I can get an updated one for future training. Good idea. Okay, so as you take a look at the parameter, if you're not using a map device, and you take a look at your little parameter sheet, you're going to notice there's going to be some different columns on the parameter sheet. You're going to have like a full name description of the parameter, and then you'll have the display name, which you'll actually see on the display. And then in another column, it'll give you the selections and ranges or a description of the functions. And so it'll say, it might say, default or whatever, from a factory default. The DFLT is the factory default column. And so if you want to look at a glance, how it's set up from the factory, you can certainly do that. And the user path. Now, the user path is how the technician is going to access the information on the display. So what you're going to do, you're going to press the enter button. And remember, you're at 0 or home screen. You press the enter button, and you'll move to a higher level and accept the parameters. You know, and some of those parameters might be details and service and so on. Then you're going to use the joystick to cursor up and down. Now remember that sideways V is the symbol in the user path on the parameter sheet to indicate the use of the joystick. So if you take a look at the little parameter sheet, you'll notice over here on the user path side, you're going to notice that there's some little sideways V's or little greater than signs. And what that is, that's your cue when you look at the user path on the parameter sheet, that's when you're going to use the joystick to cursor up or down, okay? Now, so let's do an example together. So let's say, for instance, if you've got a parameter sheet, fellas, I'm gonna have to turn my light on here. I apologize for this, but I'm gonna have to turn my light on so that I can see my parameter sheet. So as an example would be, if I go to the parameter sheet and I want to do a thermostat only enable, what I'm going to do is I'm going to find an example would be on this unit, if I have a thermostat as my main control. So what I'll do is I'll go down to my thermostat only control, and then I need to get into our thermostat only control enable. And so if I go to my parameter sheet and I go to my user display and I poke enter, it's going to take me to the next level. And then I'm going to scroll through until it says details, and I poke enter. And then I'm going to use my cursor up and down to find where it says service. And once it highlights service, I poke enter. And then I'm going to cursor up and down to inputs, press enter. And then I'm going to cursor to thermostat, press enter, and then find the parameter that says thermostat only enable, or thermostat only. And I press enter. Now, once I do that, if the display reads no, then I'm going to move my joystick left and right to get it to flash. Remember, when you get a flashy screen, that means you can change it. So you get a flashy screen, and then you move your joystick left and right to select yes in this example, and then press enter. Now at that point, what you've just told the board to do is you've told the board that you're driving it by a thermostat only. And so that's just one example of many parameters that you can find on the parameter sheet. And again, I made a little note. We'll go ahead and look for some updates on that. But in answer to that good question, there have undoubtedly been some updates as we have different versions of the board. But fellas, the result is going to be the same. You're going to have a user path. You're going to have different parameters that you can get into, and you can access it right here at the board. Or get yourself a map device, because when you plug the map device in, it allows you to access that unit by your smartphone or your iPad. So that's really what I recommend for a tool. But from a practical standpoint, if you only have one or two pieces of equipment you're working on, you can still get into all the parameters of the equipment by looking at the parameter sheet and utilizing the enter, cancel, and joystick functions. Any questions or comments on that quick little example that we talked about?
No, we're good.
Well, fantastic. Fellas, again, the parameter sheet, I apologize for being so small print, but it was the last version of it that I had a couple years ago. And so using that sheet is a pretty important skill. Well, fellas, at this time, we're going to go ahead and open the floor up if you'd like to unmute your mic. If you have any final questions or any comments on our little overview of the Simplicity Control today, hopefully you learned a few tips or two and maybe a little better understanding of the control board and how to access it. But please, at this time, go ahead and unmute your mics if there's any questions or comments as we start kind of winding down our training for this morning.
Jerry, we have a sensor question.
Mixed air temp sensor failure. What exactly is that?
Okay, what it's doing is on your economizer, it sounds like it'd be like an economizer sensor. So if you have an economizer, I believe they do have a mixed air sensor, and what that does, what that sensor is doing, is actually looking at the air it's bringing in from outside, mixing with the return air, and it's one of the things that allows the unit to calculate heat content of the air. And so if you have, there's three basic controls or three different options you can have on an economizer. One is a dry bulb changeover. In other words, it just looks at the air temperature outside and the air temperature inside and says it's okay to economize or open the economizer. Then you have what we call a single enthalpy that looks at air temperature and humidity outside and temperature inside to determine if it's okay to economize. And then the third option is what we call dual enthalpy. It looks at the temperature and humidity outside, temperature and humidity inside, and then makes the determination if it's okay to economize or not. So based on the type of control that you've got with your economizer, that mixed air sensor is going to be looking at temperature, but you could also have some humidity sensors in there as well. Now, one of the things I'm going to recommend is, especially if you're in a humid environment, and if you're going to have an economizer, I'm going to recommend that you do the dual enthalpy. That way, the unit has total control of when to open that economizer, based on humidity and temperature inside and outside. And so, but that's what that mixed air sensor is doing. It's basically looking at the mixed air temperature between outdoor air, return air mix, and determine the position of the economizer and stuff like that. I believe that sensor, that temperature sensor, is still a 10,000 ohm at 77 degree sensor, though I think it's the same calibration point. Good question. Any other good questions or comments?
I guess where is the sensor at?
It's going to be in the economizer return air housing area. And so you'll see, if you have an economizer on the equipment, you'll notice that somewhere in that area where there's going to be a place that can sense return air temperature and outdoor air temperature, where they mix together before it goes back, into the fan and into the supply and all that. So it's going to be in the economizer return air section.
I never found one more than just the return air sensor there.
Okay. Do you have an economizer on the equipment?
Yeah, and it's got dual humidity sensors in there, one outside and one in the return air.
Okay. Okay. Well, that's where it would be. I mean, if you've got a mixed air sensor, it would be in that area that's where it can sense the mix of air temperature for outdoor temp, indoor return air. In that box, there'll be a sensor in there somewhere looking at mixed air temperature. That's the only place you could have it that makes any sense. So, and by the way, while I'm thinking about that, when you guys set up your economizer minimum position, what method do you use to do that?
So we look at the chart, Joel, based on where we are climate-wise.
Okay.
And set a minimum position for the unit. Typically, in our climate, it's around 10%.
Okay, around 10%. Okay. All right. Well, there's just kind of put this in your little tool bag. There's a little easy math app that Bruce Porter made years ago. And I'll try to find it. He's also got a little Excel spreadsheet. I'll try to find it, Guy, and I'll send it to you. But what it is, it's just a little app or a little spreadsheet that you can plug in outdoor temp, return air temp, and then based on your mixed air temperature, the result of that mixed air temperature, it will allow you to adjust your minimum position to where you're actually, exactly the percentage that you want. And I'll try to find that and send that to you or show you the link on where to find that. But that's a great little tool for really accurately setting your minimum air temp. What you do is you enter your outdoor air temp, you enter your indoor return air temp, and then you have a thermometer basically in that area that is mixed, that mixed air temperature. And then based on that mixed air temperature is a direct correlation of what percentage your damper is, because you know as well as I do, if you take a look at the damper and it looks like it's 10%, it might really be 20% or 5%, you know, so just looking at it isn't the most accurate way to do that. So that's you know, something a little bit along the lines of mixed temperature as well. It's a pretty neat little tool. I'll try to find that for you and send that to you.
That'd be great. We use the match device to set them before they go out.
Okay. Sounds good. Well, good. Any other good questions or comments, fellas, before we secure for the morning? Well, guys, I'll tell you what, I've been honored and blessed and pleased to train with you guys this morning. I want to thank everyone for your attendance today, and by all means, let's continue training whenever you guys have questions, or Guy, when you'd like to set some stuff up. I sure appreciate the opportunity to train with everybody. And if there's no further questions, we'll go ahead and secure for the day. And I will have this loaded up out on the YouTube training channel here before the day is out as a recording if you'd like to review it again. But please be safe and please be healthy. And we'll talk to everybody later. Thank you.
Thanks, Joe.
You bet.
Thanks, Joe.
There you go.